Hi, this video is about the solution process. We're going to look at the energetics of forming a solution and talk about spontaneity, why some things dissolve in other things and why some things do not. So let's get started and let's just visualize what's happening. So in a solution, you have a solvent. It's what's present in the greatest amount, and that is shown here by these red spheres. And so the first thing we have to do is we have to separate the solvent molecules from one another. And so they're probably, they have some type of intermolecular force that needs to be broken, and so that we can spread out the solvent or to separate the solvent particles. That will always take energy to do that. So that is an endothermic process. So that is this delta H number 1 right here. And that is a positive delta H because that will take energy to do. And the second part of a solution is the solute, and that is present in the least amount. And again, these solute particles need to separate from one another and break the intermolecular forces. And again, that's represented here by delta H2. That is also endothermic. And so to start our solution process, we have to put energy in to separate the solvent particles from itself and to separate the solute particles from itself. But then there's an attractive force, and it depends on how attractive the force is between these solvent and solute particles. But no matter what, that is going to be an exothermic reaction, and so that is delta H3 here, and that will form our solution. And so this is endothermic, separating the solvent and the solute particles, but then when they come together, that is exothermic, and that is how we form our solution. All right, and so for this whole process, the energetics behind it would be to calculate the delta H for the solution. It would equal the sum of all of these. So this delta H1 plus the delta H2 plus the delta H3. And as you can see from this, these two are positive. These are endothermic. This is exothermic, and this is negative. And so the solution process, the delta H of a solution can, if this quantity is greater than this quantity, it would be endothermic or it could be exothermic. Okay, so let's just summarize in words. The separation of the solute particles from one another is endothermic. It's endothermic separating the solvent particles, but then when they come together to get the attraction between the solvent and solute particles, that is always exothermic. So the conclusion is that the formation of a solution can either be exothermic or endothermic. So we have got some examples of this that are very, very, very practical. And the first one is, I don't know if you've ever used these instant hot packs, but this is magnesium sulfate. Whoops, hang on a second here. Magnesium sulfate in these packs, and then when you twist it, it will go ahead and mix with water, and it becomes really hot. So the delta H for this reaction is negative. That's an exothermic reaction. And then there are cold packs. And so this one is, oh goodness, I think probably ammonium nitrate. And so when you, again, mix the ammonium nitrate crystals with the water, when you twist these packs, it's endothermic, so the delta H for this is positive, and you get that instant cold. All right, so let's go ahead and look at this diagram of the energetics. All right, so first of all, you put energy in to separate the solute and solvent particles, and then when they come together to form the solution, if this delta H3 is larger or has it's a more negative value than these delta H1s and 2s are, the overall process is exothermic. Here it would be endothermic, where delta H3 that isn't quite as large as delta H1 and 2. Okay, so now, will this happen spontaneously? In other words, without any outside intervention? Well, there's two things we have to look at. We have to look at the energy of the process. So processes in which the energy content decreases tend to occur spontaneously. So this reaction here, so where our energy, where we are ending at a lower energy, this would tend to be spontaneous. Okay, that's favorable. It's what we say, it's thermodynamically favorable. We're going to a lower energy state than where we started. But like we talked about, there can be an endothermic process that can happen spontaneously, like that cold pack, where it is endothermic. And so there's something else that has to do with spontaneity. So the energy is only one part of it. The other part is something called entropy. And if you watch the entropy videos, you understand what that is. But if you've not, the entropy is the randomness. And solutions and chemical systems like to go to a state of randomness. So if our entropy of the system increases, that's favorable. And so sometimes this randomness or this entropy factor is favorable. And so even an endothermic process can occur spontaneously because of the driving force from the entropy. All right, we would like to take a closer look at these solute-solvent interactions. In general, the stronger you have of attractions between the solute and the solvent, then the greater the solubility. So things that are polar like to dissolve things that are polar. Things that are nonpolar like to dissolve things that are nonpolar. Here's a vocabulary word for you, miscible. It means that the liquids mix in all proportion. So water is polar, it can hydrogen bond. Therefore, other things that are polar and or can hydrogen bond should be miscible with water, or they should dissolve in water. So here's a look at alcohol. And this alcohol has this OH group right here. This happens to be methanol. This part of the molecule looks nonpolar. Carbon-hydrogen bonds are nonpolar. But here we've got that hydrogen attached to the oxygen. It's able to hydrogen bond. We would predict, and we would predict correctly, that this alcohol will dissolve in water, and it does. So if we were to draw a water molecule here, here's what could happen with our hydrogen bonding. So here's our water molecule. So this hydrogen bonding would go between this oxygen and that hydrogen, and so forth. And so we can see that because water is polar, this alcohol is polar, they could both hydrogen bond. These would be very soluble in one another or miscible. Okay, so nonpolar liquids tend to be insoluble in polar liquids. So this is benzene, C6H6. It is very, very nonpolar. And even though there's hydrogen here, that hydrogen is not connected to an electronegative element like oxygen, like we saw in the alcohol. And so this is very nonpolar. It's not going to dissolve in a polar solvent like water. This is just the shorthand for benzene, C6H6. When we talk about organic chemistry, we'll talk about what this means. But anyway, this is nonpolar. It's not going to dissolve in a polar substance like water. It will dissolve in something that's nonpolar. And a lot of times, what they use for the nonpolar solvent is a lot of times they'll use carbon tetrachloride. This is the Lewis structure for carbon tetrachloride, and as you can see, it is nonpolar, and the benzene would dissolve in the carbon tetrachloride. This is a common nonpolar solvent. Okay, so conclusion. Substances with similar intermolecular attractive forces tend to be soluble in one another. And so that's where this saying, like dissolves like, comes from. So things that are similar in their intermolecular attractive forces will tend to be soluble in one another. Okay, so let's practice. We would like to know if these substances will dissolve in water or carbon tetrachloride. And carbon tetrachloride is nonpolar, water is polar. Okay, octane is C8, H18. It's nothing but carbon-hydrogen bonds. This is a hydrocarbon straight chain one that's very nonpolar. Sodium sulfate is an ionic compound, and it will split up into ions like that, and we'll have 2 sodium ions. Hydrochloric acid is a strong acid, and when we put it in water, it completely ionizes or dissociates into these ions. And iodine is very nonpolar. Okay, so what will these dissolve in? The octane is nonpolar. It will dissolve in the nonpolar solvent, carbon tetrachloride. Now, we look at this ionic substance, and we don't really use the word polar or nonpolar, but ionic substances are just extreme polar substances. Remember, something that's polar has a separation of charge. Well, here we've got a full positive charge and the full -2 charge. So this is like extreme polarity. It will dissolve in the water. Hydrochloric acid, again, those ions will dissolve in water, and this is nonpolar, so this will dissolve in the carbon tetrachloride. All right, so I hope this helps you answer questions, or if you ever wonder why does gasoline not mix with water, gasoline must be nonpolar, and it is. It's a bunch of hydrocarbons. Why are these ionic solids, why are some of them soluble in water? And it's because they separate in solution into ions, and that makes them miscible in water, and the hydrochloric acid as well. Splits into ions, and this is why, like iodine, it's not miscible in water, and so it's nonpolar. All right, well, I hope this helps, and well, thanks for watching.